we have a rocket scientist right in the wings, ready to give a talk. Igor Prikhodko is a principal engineer at Analog Devices. And the reason I call him a rocket scientist is he got a PhD from Irvine in mechanical and aerospace engineering. So I'm going to take the aerospace and say that he's a rocket scientist. So he's actually developed a lot of IMUs and inertial MEMS, over 12 patents. A whole product line at ADI is in production based on his designs. He has over 40 publications and very accomplished guy. Apparently has a very short commute to work, I'm told, by his colleagues. And the last time he gave this talk, just warning you guys, it took 2 hours. So, and it was in Hawaii. So a lot of you that wanted the next MSTC there can see him there. But he promised he's going to shorten it for us. Okay, Igor, take it away.
Thank you, Paul. So is that what I use for going between slides, right?
The green arrow.
Green arrow. Well, as a rocket science. All right. Well, so let's think of what do we know about navigation and how to solve this challenging problem. First of all, when we think of this issue, is we have to take into we have to know everything about what's going on the scene, right? So we need to know who's moving and what's not moving, right? And that's a very challenging problem to solve. So it actually takes a big effort to take out from the image what's moving. And to train neural network to do that, you have to actually pay people or humans to label things on it. But luckily, that's not what we are trying to solve here. When we go down lower level, we can find on the map, just like I was saying, what's moving and what's not. So it's a bit of easier issue to solve, but still you might need to update those maps, keep them in time, because some buildings are changing. But we are not even doing that. We will do something even more simple, just a problem of geolocalization of where you are at any given time without GPS. So that's much easier problem to solve, right? But even that takes billions of dollars to solve, and many companies are doing that exactly. But I think it's where our company can shine because we do those inertial measurement units, right? So let's look into different ways of doing that. We all know what GPS is, or in other countries it's GNSS, or in Europe and India, they have their own 6 satellites. So it gives us a global reference, your latitude and longitude. We can decompose this into velocity and angle, because that's how you can do dead reckoning, if you know your heading and how fast you're going. A different way to solve this, if you do not have these 6 satellites available at all times, you can go a different route, which is based on inertial measurement units. You need an Excel to get your velocity and gyroscope to get the pitch roll, your angles. Now, in the past decade, we have seen lots of startups who are primarily using cameras, LiDARs, and any other sensors but an IMU. So you definitely, since 2017, every car now has a camera for an obstacle avoidance and radar, right? And Google and Waymo, or Uber, they're using high definition maps to do the navigation. What you can actually do is so-called odometry, right? And it's a very old, 50-year-old problem to solve. But why we're bringing this up is because my talk is about sensor fusion, right? So how can you make a better pose estimate, given that you all have all this different fleet of sensors, right? So what we need to look into in how those sensors are complementary to each other. And that's why I labeled those few blocks in green and red. So you get pretty poor velocity estimate if you use just an Excel only, right? Same goes for the odometry. You get pretty poor estimate of your heading angles. But if you take the best of the two worlds, the velocity from any source of odometry, camera, radar, LiDAR, and combine it with a good estimate of the angles, petrol yaw from the gyroscope, you'll get really excellent system. So it would still give you local position, meaning it would be relative to some point on your map, but then you can use from time to time GPS updates to get you to back to your global map on the Earth. We're also going to talk about tight coupling between IMU and the odometry, and I will cover that later. So when we look into the market, there are many people, many players, and it's a very broad market. Where we stand out is definitely in inertial measurement units, right? But then you can expand into vertical gyroscope, into attitude heading reference systems, into an INS plus GPS, wheel odometry, and the last one is where we've been working on for the past 5 years is the any type of perception odometry. So the unfortunate news is that there is no plug and play solution. Everything is custom to a specific card, to a specific ecosystem. So there is no there is no way you can just buy one thing and plug it in your car. So even worse, that you have more than sometimes 100 states in your Kalman filter or any sensor fusion type filters, and you have to deal with a convergence issues, with latency issues. So one of the biggest issues is latency, right? You get a huge data from all your sensors, and unfortunately, every one of them giving you an information from the past. And it could be as worse as 100 milliseconds. That's very typical number for a GPS. So even the data from camera will give you with best GPU on the order of 20 milliseconds. So how do you deal with that? Because, for example, when you move with a highway speed, 65 miles an hour, in that 100 milliseconds, you have covered 3 meters. And you could have killed someone in that time frame already. So, and needless to say, all the feedback and navigation controllers, they need to have less than 5 millisecond latency to do the dead reckoning and navigation in closed loop control systems. So how do we solve this? We've been thinking about this issue for a while, and we came up with a so-called trusted motion unit. So we have the regular inputs to the system, like GNSS, wheel speed, visual odometry. It all goes to an extended Kalman filter. But what we've came up with in hardware, and that's why I say hardware, because there are many different ways to solve this in software, but it's always looking into future, like your sort of crystal ball. You have to look into the future. So we actually rely on the inertial measurement unit to give you the most accurate information about your position, because it has less than 4 millisecond latency. It gives you really fast update up to 4 kilohertz. Plus, combined with our low latency kinematic filter, we can put up to speed all other sensors. So, and everything here is going to be synchronized in time. So how is it different from your typical conventional approach? Is like I was saying, we do use an inertial measurement unit as our core sensor to which we time, align, and buffer the data from all other sensors. The beauty of that is that you can actually use very cheap GPU processor. You don't need to use NVIDIA Drive AGX, which costs $50,000, or you can get by with a much smaller Jetson Xavier, and that's just because you don't have to have 60 frames per second coming through camera to update all the errors and biases from your, say, gyroscope. Because you have very long-term stability, or at least if you buy it from our company, you will have very good IMU, so you don't have to update the drifts that fast. So you can get by with maybe 10 seconds without changing for drifts in the IMU, and that's what would let you to use the lower GPU processor for this task. I think that was also covered by talk from Meta today, this morning, where Dork said that they're also looking into low frame rates to save on power and the GPU processor time for their AR glasses. So this is a slide where it tells you that if you combine an IMU with the perception odometry, you can achieve same performance, say 20 centimeter accuracy of the pose estimate if you use your IMU with a camera odometry. You will reach 20 centimeter after 1 minute with a lower grade IMU, but you have to have much better IMU if you use only that to do the same problem. Right, so let's get to the real data. So we have a car that was driven on the real roads, and we've installed the dual IMU, some low-cost IMU and high-end IMU. We did install a differential GPS with very precise time stamping. We did put LiDAR, radar, and stereo cameras on top, but I'll be mostly talking about how to use camera with an IMU because I don't have 2 hours. So on the right, you see it looks much smaller in real life. That's why I put 5-inch scale on this. But we did use a very low cost GPU, NVIDIA Jetson Xavier. So we have inputs from car and CAN bus. We do get velocity. We do get all other inputs, and they're all time synchronized. So with that module, we get some data, and inside that module, this is what we call trusted motion unit, right? You get your CAN inputs, which could be not just the speed of the vehicle, but it's also steering angle, although we did not use that in this work. You also get inputs from your GPS U-Blocks antenna, and we save all the data to a micro SD card. And it's also powered by 12-volt wall plug, sorry, the car plug. So here you can see we use 2 different IMUs, low cost and high cost. So if we deep dive into how it's working, on the left you see on that trusted motion unit PCB, we have only extended Kalman filter. All the software will go there, our low latency kinematic filter. And then on the left block, you see what's on the NVIDIA Xavier. There you have your mapper, tracker, and ways to find the features from frame to frame from left and right cameras. So we only feed those feature points to the TMU block, And actually from VO, you can get, like I said, a full 6 degree of freedom pose estimate, but we would be only using velocity, would go to this synchronizer block. On the right, you can see our GUI. There you can see the sampling rate. There we went with 1 kilohertz sampling rate, our end-to-end latency of here 0.6 milliseconds, which we're very proud about. And on the right, you can see different modalities. So we're going to be discussing all different sensor modalities you can use and play with. So GNSS, IMU, wheel speed, and visual odometry. So let's see how we've done. That's just a few months before this talk, we went into Cambridge, and that's very close to like where we are now. That's a track about 2 miles long. What we wanted to show here is that what is our error growth with time. So we all know that the drift in the IMUs, they grow with time, but so do any sensor from camera. If you do visual odometry, your error or the variance of your position will grow with distance. So we wanted to know what's the trade-off. And when you pair your visual odometry with an IMU, now what is the best time frame? And what we found is that for a short period of time, say less than 10 seconds, you can use an IMU, right? But for longer period of time, you can take advantage of the visual inertial odometry. That may seem to be a very trivial, but there are a few different things we will cover on that topic. So one of the things we've been trying to do, as I said, is to demonstrate very low latency. So on the right, you can see our data from real run, and the mean value was of that end-to-end latency between all sensors was 4 milliseconds. And that was despite that you have 100 millisecond delayed data from GPS, 50 millisecond data from your CAN bus, from your wheel speed odometry, or from your visual odometry from camera, where you have 20 millisecond low latency, sorry, high latency. So that's actually was done all in hardware. And that's what we can sell to a few customers. So now, how does tightly coupled VIO works, and what is it? So instead of moving, or instead of doing a vertical search pixel by pixel in your camera to find that one feature from one frame to the second frame, you can actually use an IMU to tell you where to look forward. So an IMU can tell you, because you're going with a certain speed and at a certain heading angle, you can tell where to look for that same feature from the past, where it will appear in the next frame. And so that is shown on the right. You can see in the blue circle where an IMU tells you where you're going to be, or that's some feature, and red is where that feature is. And by feature, I mean anything that you see a hole or an X mark or something on that car or on the house. So that's why if you do tightly coupled visual inertial odometry, you can get by with very cheap GPU. But it's very hard to do in software. So finally, let's get to the real data. When we combine an inertial measurement unit with just a wheel speed only, we look into the 1 sigma error. After 10 seconds of GPS outage, you can get to maybe 15 centimeter. And that's what we looked in the theory, and it matches with our real data. Now, after 60 seconds, you will get on the order of 1 meter error. So unfortunately, wheel speed has its own issues. slippage, skidding, even the tire size may be an issue because it may change with the speed. Now, when you combine this with your visual odometry, you can get to the almost same performance, 26 centimeter error for 10 seconds and 1 meter for 60 seconds. And that's what I told you. It wasn't trivial if you combine the visual odometry. Why is that the error after 10 seconds is higher than for a simple case when there's only wheel speed? And I will cover that at the very last. So you may think that if you combine two sensors, you get the best of the two worlds. Sometimes it doesn't work that way. But on long term, in long distances, if you combine the two, it will get better. All right, so how did we do relative to the state of the art? So it doesn't matter 1 meter or sub-meter accuracy, it's all relative with distance, right? So I didn't even tell you how long we've traveled. So that's why we have to look into the relative error. It's your positioning error divided by distance you've traveled. That's what you see on y-axis of this plot. And the path length on the x-axis is how far we've traveled. So KITTI, or KITTI, is the benchmark that's used by most companies to know where we stand. It's just one data set that all companies use to see how their method is doing. So we've did the same. We've applied our methods, and we wanted to see where we are. So this graph actually shows we are no worse and no better than the best of the best method that's being done in the world. I mean, not everyone is using KITTI for the benchmark, but at least the one that's been published, we're no worse than them. So we did achieve on the order between 0.1% 0.1 to 0.5% error. And now we have shown that we can even get better than that, but we will cover that in a different topic. All right, so since I'm a gyroscope person, I wanted to see how can gyroscope help. So on the left, you see if we use a 100-degree-per-hour gyroscope, and we don't sell those, that's why I had to do an emulation. So what you will find out is that you will, your first 100 meters of your traveled distance, your error will be dominated by the camera errors, and then after that, your gyroscope bias error will dominate. So this is not the case when you get really good gyroscope from our company, because then the error is so low, everything will be dominated by the visual odometry errors. And like I was showing on the previous slide, we're no worse than the best state-of-the-art visual odometry method that's been used. So this slide here is showing you how error growth with time for different sensor modalities. I was trying to explain earlier that if you do use NIME only, your error will grow cubic with time. When you combine it with any other sensor, wheel speed or camera or both, you will get it down to square with time. So it's better. And up to 10 seconds, if you do a dead reckoning for 10 seconds, you can only probably use NIME only. Very cheap, don't need to do any sort of visual odometry methods. But for minute of GPS outage or more, you want to actually combine it with wheel speed or visual inertial odometry, because in that case, you'll get sub-meter error as opposed to 7-meter error. So this is my final slide here. Why do we have to combine wheel speed and the visual odometry? Well, the answer is because they are complementary. What I mean by that is that from the wheel speed, you get very coarse information about velocity. So at very low speeds, your your wheel speed is very coarse and it's poor. However, at higher speeds, you get really nice nice accuracy. That's not the case with the visual odometry. Yes, you do get much better velocity estimate, but at higher speeds. Sorry, I meant since you get 60 frames per second, right? It's always constant. But as you go with higher speeds, you get less frames per. You see much less things on the road when you go fast. One way is to have maybe 120 frame per second that you can get by and solve this issue. But normally, those cameras only give you 30 frames per second. So that's why if you combine the cameras which are good at low speeds and wheel speed which are good at high speeds, you'll get both of the two worlds. And I guess that's it. What we've learned is that you can get by without high definition maps, no SLAM, no neural networks. If you do use camera odometry with wheel or LiDAR, and then you can get even with cheaper IMU if you do the sensor fusion properly. I would like to thank all the people who I've been working with because it's very hard to do it all by your own. First and foremost, I would like to thank my manager Sam, and of course Mike, Judy, and all the colleagues from here who worked on that. One person who is not listed here is I've been working with her, and that's where my story about DEI, not DUI, but DEI comes from. So she was working with me for before COVID, and she was from LiDAR group. And at that time, we were big at LiDAR. We thought it's going to solve all the issues, will save the world. But at some point, we thought that we may do more MEMS rather than LiDAR. So I was trying to help her out and move to our group, MEMS group. So I was working with her, and she's from Europe for over 6 months. And I've poured all the knowledge I had about how to do the best gyroscope you can. And she was a fast learner. So I was very happy that she would be working for our MEMS group. Unfortunately, at some point, we had a layoff, and they decided to let her go. But she is now a highly respected manager doing the deep sensing in Facebook. And she's probably getting twice the salary I'm getting now. So that's my story. Well, thank you very much.
All right, do we have any questions? No questions. Yeah. Tim?
Thanks, Igor. It looked like on slide 23 there that when you combined the wheel speed sensor and the visual odometry that it got worse than performance with just one of them?
23.
Blue line, right? That's the two together. Did that get worse than just the wheel speed sensor itself?
Yes, that's right. So I would say that's why I actually brought those standard deviation broad lines. It all very depends on the features you have on the road. So it's actually not fair to say that, yeah, you can look into the median, but actually it's all noise. I couldn't really tell if you have just the wheel speed or just the visual odometry, and both of them, they kind of the same, all of them in the same ballpark. I would say that at a very short period of times, there is practically no difference
Evelyn from G. Yes, very good talk, Igor. Yeah, good job. So, question about you mentioned that you're using kind of tightly integrate inertial sensor help reduce the computation burden on the VO side. So, question is, if you have seen that you have a lot of moving feature or highly dynamic situation, do you have to increase the computation power to handle that situation?
Right. So typically in that case, you want to use not just one camera, but multiple cameras. Not just one looking front, but some companies use the entire, left, right, back. But typically, any car by now, they have front and back cameras. So for that you actually will need to have a higher GPU, but fast dynamics will be captured by actually a gyroscope, right? Because it will tell you we can use that, because if you do a really fast turn, the gyro will tell you that. And that's what can help for the camera to switch from very upper right corner to very low corner, right? That's how tight coupling can solve this issue without actually changing the frame rate or anything that drastic. So I think we can keep the same GPU power requirement, but just more rely on an gyro to tell you where to look for that feature in frame.
So a lot of people probably in the audience drive cars, and you guys are working on navigation stuff and IMUs. So when are we going to see a car that can really, truly drive itself?
I wouldn't want to see that because I know how it's all done and where things can go wrong. Just like if I was a Boeing person working for Boeing, I wouldn't want to fly their planes, but I'm just kidding. Well, really, it was a hype. The promise was by year 2025 we would have them. But unfortunately, many companies are backing out, and many startups, they actually were dissolved. We worked with a few companies that no longer in business now. So it's a very tricky business. It comes to the government and it comes to states. So it's not that easy.
So in our lifetime?
Maybe.
Maybe. All right, let's give Igor another hand.